All right, welcome. So we have an extra day that I don't usually get in the fall semesters. In the spring semesters, we get an extra day of class because there's no Thanksgiving. And so I have made an extra lecture that I'm not going to test you on, but I have a fun topic for us. All right, so it's worth watching. It's going to make your life easier when you get to future classes anyway. It's just I think it's an interesting thing. So I'm going to teach you how to reverse engineer code, reverse engineer binaries, and how to patch them. All right, so it's like I'm going to teach you how to hack essentially. So please do not get caught by the FBI or anything. If you do something silly, that's your fault. But yeah, I want to teach you how to take apart a binary program and mess with it. All right, so here, to get there, I need to talk about a feature of C++ that you have not yet learned. It's something we do not teach because it's a horrible feature, but it's something you need to know because it's what a CPU does. So there's something in C++, there's a way to make a label. It's called a label, like label 1. And you put a colon after your label's name, and you can put code, and then somewhere within, you can make other labels too, like label 2, ... colon, put some code. You can section off pieces of code with labels, and then you can say go to. There's something in the language called go to label 1, and it's you can roll your own loop essentially. So what it does is whenever it sees this, it just takes your program right back to here and it starts running the code from then onwards. All right, we go back there. You see how you can make loops with that? You could say in here, you'd be go to label 2. So this is a way to loop in a very weird way, all right, but it just kind of warps you to different places in the code, all right? It's very hard to reason about, and that's why we don't teach it. But now you know. Please never use it. But CPUs use it all the time. When you learn assembly programming, which I'll teach you a little bit of today, in CSCI 45, you're going to need to understand this stuff. So here's a sneak peek. All right, so here's a program that's going to use goto. Just to give you some practice with it, let's make a program that loops and counts from 1 to 10 using goto. Okay, so instead of the normal one, int I equals 1, let's have a weird looking loop for a reason, while true, because this is going to be what we kind of translate into goto land. So let's print from 1 to 10 though. All right, so cout I, and then I++. And so this is infinite right now, but eventually when I gets too big, if I is greater than 10, it's bigger than the number I want to print out, then I'll break. Does that make sense? This kind of loop, it's going to print from 1 to 10, and it's just a weird way. All right, this is a normal loop still, but it will print from 1 to 10, and now let me translate this code into uses of goto and labels. So instead of this, I'm going to do the same. I'm going to take most of this code in place, copy it. And so here, I'm going to say, instead of while, it's loops without loops. So instead of this is going to be called, I'll call this loop start. It's the beginning of the loop. That's the start label. And then, and I don't need this. I don't need this. And then there's no concept of breaking out because there's no loop that we're in right now. And it's if I is bigger than 10, what I want to do is go to the end of the loop, I'm done. Here's the done label. So go to done. Does that make sense? And then otherwise, if we make it through and we run an iteration, the way that while loops run is they always go back to their body, right? They always go back to the start of them to retry the condition. All right, so go to loop start. Does that make sense? This is the same as this code. Does that make sense to us? So we made a label, this is the start of the loop. What does a loop while loop do? It's always check your condition, stop when you're too done, right? When you're close to being done. All right, so there's that, and yeah, here it is. There's the start of the loop, which just skips over that the first time. It's all right, I is not greater than 10, so I'll run this, then I'll go to loop start. I'll just keep on repeating, skipping over this the first few times, and eventually when I is 11, we don't want to print it, we go to done, which ends the program. So that's labels and goto. Disgusting, but it works. All right, and that's how CPUs work. They have instructions inside the CPU to warp you places, and so that's what your while loops and your for loops turn into. They turn into uses of goto inside of the CPU. All right, so that's what we're going to see soon. All right, so now you know. And now I want to talk about how CPUs execute stuff. They execute what's called assembly code. That's the lowest level of code. we can look at it as humans, but really it's ones and zeros. We can look at the English equivalent of it, essentially. All right, so we're going to make a Hello World program, and for unfortunate reasons, I'm not going to use the cout. All right, cout looks a little weird. I'll show that to you in a second. I'm going to use the C language's printing function. It's called printf. All right, it lives in C_IO. It's called printf, and it just prints a string if you give it a string. So it's just normal. It takes a C string and it prints it. For weird reason, it returns an int. You usually don't use that. So okay, here let's talk about that. Let's make that program. So I'll call this hello.cvp. All right, and so instead of IOStream, I'm not going to use cout. I'm going to use c_IO. All right, and that'll give me printf. Because cout looks really weird for what I'm about to do. The first time you learn it, it's better to use the old C language stuff. So here's hello world being printed. Hello world, exclamation point, new line. That's just the C way of printing stuff. There you go. And so let's compile and run that, just to prove that to you. And so here it is. There's my executable, there's my binary file. Oops. Right there, I've just run it. So it prints hello world to the screen. Nice. And now let's look at the CPU instructions that make this program up. So like, that's what a compiler's job is. That's what G++ does when I compile. It translates my code to what's called assembly code. It's code that is specific to my particular CPU on my machine. I have an Intel processor, so it's going to be Intel assembly that it's going to generate. All right, and you can tell G++ to like not go to the final binary, but stop at the assembly stage. You do -S for assembly, and there's different flavors of Intel processors assembly. We want the Intel version, so we say it like this: G++ -S. Tell it to give me the pretty kind of Intel assembly, and what it will do is generate this hello.s file, S for assembly. Apparently .a was already taken, so they used .s for assembly language. And so this code got translated into this file. It's disgusting looking. So, boop. Here's my program. It got translated into this file. It looks a little weird, all right? But this is assembly code, all right? Each line is an assembly instruction. These blue things. These are instructions for the CPU. It knows how to, like, there's a binary encoding of this to do stuff, all right? And so there's like, here it is, it's storing the string in memory. It's putting in the memory before the main function. It's just a label. Here's where the main function starts. So that's why I needed to teach you all those other things. So yeah, all these names that start with R's, RVP, RSP, RAX, RDI, those are little, essentially global variables that live inside of the CPU. Every CPU has, every Intel CPU at least, has these things with these names. They're little variables that you can put anything inside of them, and they're called registers. All right, so here's a picture of your CPU. And registers are very important. That's where you put all the data that you're working on as you're running your program. You want to get it out of memory and into registers. Like you can put a 42 there into a register. So those are your registers. That's what they're called. Again, I'm not ever going to dream of testing you on this. All right, you don't have to understand any of this. It's just fun. All right, I think it's cool. I like talking about it. So I hope you enjoy. So registers are like global variables. You will eventually need to understand this for CSCI 45. All right, that's what you learn in CSCI 45. Yeah, they're like little global variables for your CPU, and like you can put stuff there. All right, so for example, it is calculating where this string is because it's going to call this function. Here's the call instruction in assembly, and like you have to set up the argument to the call instruction, and actually swapped out printf for a simpler function called puts. It actually saved a byte that way because it's only storing the string hello world without the new line. Puts is a function that like prints a string and then a new line at the end of it. So actually the compiler is like, hey, you know what? I'm not calling printf. I'm going to call put string instead. All right, so that's what it's going to do. So we have to have a way of getting this string into like a register because that's where you tell the CPU like, all right, that's where it starts in memory. Now go call puts on that string. All right, that's how it's doing it. It's passing along the C string because it's a C function. And so it's got to put in a register this string and its location in memory, so it's like LC0. That's where it goes. And so it's storing it. It's like trying to calculate that offset in memory. And it's placing that into a register called RAX. And then it's eventually, for some weird reason, moving that into a register called RDI. And RDI is where you put your first argument to function calls. All right, that's just how it works in Linux. So RDI is where the first argument goes, and that just got moved to there. So hopefully you can kind of read that a little bit. It's weird, but like it's moving that value. That's like where the string is in memory into RDI. That's your first argument and the only argument that puts needs. So it's going to call that function, and it goes off and prints the string to the screen. And then the rest of this is like returning 0 to return from a function. Like this is the main function. To return 0, you put 0 in a place, it's a register called not RAX, but it starts with an EAX, because it's an int size thing. And then you say ret to return back to whoever called you. So yeah, that's what you do. That's kind of the process. Hopefully that made a little bit of sense. It's completely okay if this is going over your head. It's just fun stuff to think about. All right. These lines with dots, they're just like stuff for the assembler, the thing that translates assembly code to machine code. It's like helpful stuff for that, but these are like the real instructions, these blue things. So yeah, I think that's most of what I wanted to say. You see there's some extra information about like the compiler and everything that's like hidden inside of your program. And so it's all secretly there. If you take the compiled file, which is just hello, and you look through it enough, it's disgustingly long. There are no like new lines or anything. If you scroll through the contents of this, you will eventually find the hello world string. It is in the file, like the binary file. It has to be there, naturally. Yeah, that's assembly code in a nutshell. Those are registers. Let me show you like how people like pick apart those things and like reverse engineer what was really happening. So first of all, say you want to be a hacker, or you work for the government and like you want to solve like you want to like pick apart a virus or something. What you're going to be given is never the source code. Nobody's giving you a CPP file. They're not giving you even an assembly file. They're giving you just the binary file, right? Especially like, and same is true when like you buy a video game or you pay for Microsoft Office or something. Nobody's giving you the source code unless it's an open source piece of software. Everybody is just giving you the binary. You just like double click it and run it. Does that make sense? It's like all you get, you have no .cpp file if you're trying to reverse engineer something. You just have the binary itself, and you somehow have to like open it up, oops, like this, and like understand it, like take it back to assembly code, more or less. There's ways to do that. All right, that's what I'm going to teach you now. So we want to be able to like mess with stuff. Like we want to reverse engineer our code. We want to get the assembly back out to change it. Maybe we want to change the contents of the strings, like print hello instead of printing hello world, print something else. So here's the first thing. Let's patch the binary. Let us change, instead of printing hello world in our hello program, let's change it to print something else. All right. So let me show that to you. What we're going to do is there's a program called XXD, and that will take apart our program and produce a it's called a hex dump of it. All right, it's going to translate our program to hexadecimal. So here, let me go back to this. It's just a terminal program. It's called XXD, and you give it a file name and maybe an output file name. And what it does, it creates what's called a hex dump of the program. And so it makes, like, you know, when you open up hello in Vim, it's disgusting looking. It turns this into the hexadecimal equivalent. So it's like the binary equivalent so that you can read it as text. Okay? A picture is worth 1,000 words. So let me show that to you. So what I'm going to do is I'm going to say XXD hello, and it produces a file that looks like this. It's really pretty. It's just the contents of the binary in hexadecimal form. So here, let me show that to you. That's just a file. So here it is. Sorry, without the colors. At the left side is like offsets into the file. So like offset 0 into the file. And then here's the hexadecimal contents of the file there. Does that make sense? So like the very first byte is 7F. And then like this is like the actual binary of everything. And apparently like the very first thing is, it actually does say elf. That's the characters for elf. And then like you scroll down, but like this is like the offset into the file, like hexadecimal offset. Here's the hex part of the file. All right. And then here's on the right side the ASCII equivalent if any of these were actually meant to be ASCII characters, and usually they're not for most of the file. But if you scroll down, like this is just garbage. GNU means something. This stuff means something. It's actual text. You can scroll down enough to eventually find our string. It's in the program somewhere. Our hello world is somewhere. You scroll enough. Did I pass it? There it is. There's our hello world. Do you see that? So it starts at offset 200. 0, 1, 2, 3, so 4. So offset 2004 in the file, in hexadecimal. Does that make sense? So here's our hello string in ASCII in hexadecimal. And we can mess with, through XXD, we can change these bytes and rewrite the file into a brand new binary. Does that kind of make sense? That's what we want to do. So yeah, let me produce, if I say XXD hello and then give it another file name, it will output into that file name. Hello.hexdump is what it's called. So if I look at that, here is the hex dump. Oh no, it took it as, excuse me. Oh gosh, what do I have to do? It took it and it gave the colors. It produced the colors. So here, I guess the easiest way to fix that is to do this. Oops, XXD. That's in the manual page probably. I don't want the colors. Can I do that? I can say no color, or let's see. Disable the colors. Maybe the -r would work, but here's one way to do it. I can say XXD, give it that, and then here's the file name I want to write to, just like that. In theory, that should work. And get rid of the colors. Yay. All right, so here's the file as a hex dump, and you can scroll down, you can search for it, because it's got the ASCII equivalent over here. So there's my hello world, and other pieces of this is like the code itself. Like these are just zero padding, a bunch of zeros in binary. But like some of this, like maybe this was the code. It's a binary version of the code. Isn't that cool? So what we can do, one thing that we can do is use this hex dump to change the string. So you can't write over here, that doesn't do anything. You have to change this stuff, and then you can ask XXD to run in reverse and remake the binary, if that makes sense. So let's change this to be something else. Because we're going to be overwriting memory inside of our binary file, we cannot make the string longer, because like if you go after hello world exclamation point, if you go after the exclamation point, like here's the null terminator for the C string, if you go after that, you're writing to some other memory, which was maybe some other global variable that was necessary. So don't go right after it, and you can't change the length of the file either, because like it's looking for the same length of the file here. Can't change that. So all we can do is make a shorter string or the same length string. Okay, does that make sense? So that's what I want to do. And let's change it to be like hello CSCI or something, because that's less space. CSCI exclamation point, and then we'll change this to the null terminator. Like that will work. Does that make sense? So we just have to write ASCII values. So let's make it have, say, hello CSCI. So let's go to the ASCII table and figure out in hexadecimal what these things need to be. So there's a nice little, instead of following this, I guess we could follow this. We're going to look in the hexadecimal place, because we're writing hex codes. So like here's the H, for example. That's the 48 is the capital H, right? Or no, I might be off by one. Oh yeah, it is 48 in hexadecimal. So it's the hexadecimal, it's 72 in decimal. So 48 is the H, and then there's the E, L, two L's, right? O, comma, space. And then here, instead of world, let's say CSCI for fun. So that's going to be 43. 43, and then S is going to be 53. And then another C, so another 43, and then a capital I, oops, is going to be 49. And then we can just like take the rest. This was, here's the exclamation point, right? That's the 2-1. We want that still. We can prove to ourselves it was 2-1 in hex. So there it is, 2-1. So let's just put it here now, because we went after the I, right? 2-1. And then we want to end the C string. It's a C string. And so we put the null terminator character. This would be another exclamation point. Then null terminator, that was the old string. If we put 0, 0, that's the null terminator. That's our \0 in C string land. That's hexadecimal 0. It's the byte 0. Okay? I hope that makes sense. And so yeah, I've just changed the contents of the hex dump, and XXD, we can ask it to run it in reverse. So it's -r. Run it in reverse, and here's the file, and write to some other binary file. So here's what we'll do. We'll say XXD-R on this modified hex dump file. Changing this over here doesn't do anything. You got to change the bytes here in the hexadecimal version. And we'll call it, I don't know, hello2. Hit enter. It's going to make a brand new file called hello2 that I've changed the bytes of. And so instead of the /hello, running that produces hello world, I've changed the place in memory that hello in the file itself, where the hello world string was saved. It'll go there and write the new stuff to the screen, and it finds the null terminator. It just prints just that, hello, comma, space, CSCI. Isn't that fun? So like, if you lost the contents of your CPP file, you can go into the binary itself, change it, modify the hex dump, change it to something else. I think that's so cool. All right. That's called binary patching. We've patched the binary. We've changed it to something else. All right. So I hope that makes sense. Now for fun, let's just let's do a example of like password hacking. So let's make a silly program that asks for a password, and we will we'll try to hack it. All right. So let's make a couple files for password protection. So here's one. Let's do, again, no IOStream for a reason. It just looks weird when you're first learning it. And then I want C-string. We're going to do C-string stuff, no C++ string anything. So just function calls, not method calls. Those look a little weird when you talk about assembly. So yeah, here's what we'll do. Let's have a program that takes command line arguments, int argc, char star argv, bracket bracket, and we'll have the user give us their password. Just like this, we'll say like /password, and then they'll type their password here, and then we'll get that. It's going to be an argv of 1, right? So argv of 1 is going to be the password, and we can compare that in a C-string way to like what the password should be. So like this is the program. Like let's pretend that we don't know that this is the real program, but we'll just do it for fun. So if the string compare of argv1 and like let's say that the secret password is this password 123. If we want those to be equal, to unlock, it needs to string compare gives back 0 when they're equal, right? So if that's correct, then printf access granted. Otherwise, printf access denied. Won't that be fun? So yeah, there's my silly programs using the C library stuff and C string stuff. But again, well, you have to actually give a password. Hello. So it says access denied when you do it wrong, but when you do it right, password 123, it will say access granted. And so let's pretend that we weren't given this code, right? We pretend we didn't write this code. It's like some special things, like a virus we want to hack and like analyze if we work for the government. So we're just given the binary file, right? We're just given the binary file, which has no code at all. It's just the binary. We can hex dump it if we want. That might help. But go looking at all the strings inside of it that look like English. But you're just given the binary file if you're a reverse engineer. You are just given a binary file. There is a way to convert that binary file back to assembly code, back to like, give me the CPU instructions in a human readable form. That is called objdump. You can say objdump to -d for decompile it, give it back to assembly. So that's what we can do here. All right, so I'll do that. You can extract assembly from your executable file, and let me talk about it. So let's take this password program and objdump it. All right, objdump -d, but I also want it to be pretty, so I'll do all this. -m intel as well. -d, and then I'll call it the password program, and this kind of spits out for you assembly, and we can save that into a file. I'll call it, I guess, password. It's .s, right, for assembly. So there's that. That would work. And so yeah, let's take a look at this file that we just made. We created assembly out of the binary program with this objdump command. That's pretty cool. So here, let's take a look and see if it's useful. Password.s, like disassembly. So here's init, that's before main. If you scroll down, you'll eventually find the main function. Start, where's main? There it is, here's the main function. Here's doing stuff, and you can see that it's calling string compare, see that it's calling puts to print something again. Again, printf got turned into puts. But let's start talking about this. So here's the other program again. Password. Pretend we didn't actually know that this was the code though. We didn't have this code. But here's like what's going on, and let me try to show you that this is the assembly that corresponds to this code. All right. So here, I guess what I want to show you is let's see here. Let me just scroll through my notes to make sure I'm talking about all the things I want. So let me just like go through all what these lines are doing, because that's what you would do as a reverse engineer. All right. So this instruction is not very important. So let's start with this one. So this says push, and this is starting to mess with the stack. There's a stack deep down in memory, and the CPU knows about it, and like this is a CPU instruction that pushes whatever is in the RBP register onto the stack. So it saves it so that we can mess with RBP. Saves RBP on the stack. Yeah, let me just walk through what all this code is doing. And then this line, this one moves. You read it kind of backwards. It's like an equal sign almost. So it says it puts RSP into RBP. So like we saved the old one, now we're messing with it. Put RSP into RBP. Put RSP is a special register inside of the CPU that always holds the address of the top of the stack. All right. Put the address of the top of the stack in RBP, special place. And so like that's kind of what it just did. And the top of the stack can grow or shrink. If you say subtract 10, it's really 16 in hexadecimal. Subtract 16 from RSP, that will move the stack pointer up so that you can put other stuff there. It's like what just happened on the stack was, all right, we did this. Like here's the stack, there's other stuff below us on the stack, but what this line just did is this pushed RBP onto the stack, so it's like the old RBP because it's about to change it, old RBP. And then RSP just like automatically points to the top of the stack. So here's what RBP, here's what RSP is pointing to right now, is the top of the stack. And then this moves RSP into RBP. So RBP is also going to point right there. RBP. And then now we're going to mess with the stack some more. It's like subtract 16 from the stack. So that it has more 16 extra bytes of memory. So this is what we just did. We made more space on the stack for more stuff. Like it subtracted 16, and now RSP is sitting right here. There's the new top of the stack, and now here's empty space that we can put stuff in. That's what it's doing secretly. And here it is using up that empty space. Like, all right, go offset a little bit into RBP and save EDI there. It's like this is going to, these brackets mean dereference pointers. And like save also RSI there, right? So EDI goes here at this place, like it saved EDI there on the stack. And then in the other spot, it stored RSI because it's about to change those probably. Save those into the stack. That's kind of what's going on under the hood. You do not have to understand this, but that is essentially what's happening, and you have to understand that if you're reverse engineering, right? Like, okay, that's what's happening, that's what's going on. So yeah, what this line does is RSP equals RSP minus hexadecimal 10, which is 16, as that just made new room on the stack. All right, so make room on the stack for 16 bytes of memory. And then it's going to use those things. So it's going to move this guy, EDI, into a place on the stack. So it saves EDI on the stack. There's that. I don't know why I switched from assembly level comments to C++ level comments, but it's supposed to be like a single number sign like Python. That saves EDI on the stack. And what EDI holds is argc. That's just what happens with main functions. That's how they got compiled. So EDI holds argc on the stack. For some reason it needed to do that. Got compiled into that. And then this one, RSI, the next one, that's your argv. That saves our argv on the stack just in case we need it later. All right. And then let me just walk you through the rest now. Now it's saving. Now for some weird reason it's getting argv right back out of the stack, right? Because it just put it there and into RAX. So here is essentially what it's doing is it's setting RAX to argv, and argv is. Sorry, I just messed with my microphone. Hopefully you can still hear me. There we go. So what it just did is it stored argv in this RAX register, and it's argv is a pointer to the beginning of argv. So right now it holds the address of argv of 0, but we want to go to argv of 1 eventually in code. So watch it do that. So here it is. It's offsetting that address by 8. So this is saying RAX equals RAX plus 8. That's what that line is doing. And that is exactly the address of 1 char star later in argv, if that makes any sense at all. Now RAX holds the address of argv of 1. Does that make sense? That's what's going on, and that's what I'm about to get, right? I need that. I need that string. And so I need a pointer to argv of 1. So I need to like dereference it, and that's what this next line does. It dereferences RAX. Those brackets dereference it, and like it stores the dereference thing back into RAX. All right. So what that did, you can't do this in C++ because the types are wrong, but you can totally do this in a CPU. You say RAX equals star RAX. So now it holds argv of 1. It holds RAX, holds the first command line argument. So that's where the password is. It just got the password out, and so that's what we'd be concluding as we're doing all this fancy reverse engineering. And then it's going to do some more stuff. All right. Then it's going to go somewhere, and like the ops dump was telling us, it's going to go to address 2004 in the code, in the binary, and it's going to store the address of that into RDX. All right. So the RDX will be set to the address of something, whatever's at address 2004, like it's the address 2004, 2004 in hexadecimal. What is that? Well, we can do a hex dump of our binary to see what's there, can't we? We can say, all right, xxd on the password program, write it to password.hexdump. Let's go look at that. Isn't this fun? And we can go to offset 2000 because it's always like that. Go there, oops, boop. And what do you know, at offset 2004, so that's 0, 1, 2, 3, 4, so starting there, is a C string that holds our password. So that's, you could just, that's one way to hack the program, I guess. You've now figured out the password. All right, that's, and then you have the other strings here, access granted, access denied. So hopefully you can see how that's being used. So that's setting this RDX to the address of the password string. All right, and that's what we have concluded. And then, yeah, let me just like write out the rest of this. So like we are now unpacking the program. All right, so go back to the program itself. Again, you assume that you never had this to begin with, but it's useful to teach it to you, just to show it to you at the same time. So all right, we're working on this line. We just got this guy, we just got this string into different registers, and now we want to compare them with string compare. So here's what's about to happen. We're about to call a function, string compare, and the arguments go in RSI and RDI. All right, so let's see here. In the right order though. So RSI is getting set first. It's getting set to RDX, which is the address of the password string. So that's the second thing. It's actually the second argument goes in RSI. So RSI equals password string address, and that's our second argument because we're setting up a function call right now. And then RDI gets whatever's in RAX, which was argv of 1. Does that make sense? It's working. All right, slowly but surely. Equals argv of 1. That's our first argument. And those are just pointers to the start of those strings in memory, and we're going to call string compare on them. So we call string compare, and that's what happens, right? We're calling string compare. And the answer for any function call gets returned in RAX, right? Returns answer in RAX. Because it's though only a 32-bit thing, it's just an int that's being returned, it's going in the lower half of it, which we call EAX, all right? And so that's why it's looking at EAX now. So it's testing it for whether or not it was 0. That's what this line is doing in a weird way. Test means like check if it's 0. At least that's how I want you to imagine it right now. So what that does is it's really doing a bitwise and. Does a bitwise and on EAX. It's doing like EAX ANDed with EAX, and it's like, was that 0 or not? So this, then it says JNE. Jump is go-to. It's the go-to of assembly, of Intel assembly. So it's saying JNE, saying jump if it's not equal to 0, essentially. All right, that's what it's doing. So this is the same as really JNZ. Those are equivalent in assembly. It's saying jump, which is really a go-to, to if non-zero. That's what it's doing. If the answer was not 0 for this bitwise and, then that's going to be our else case, right? That's where we're about to go. So go there, go to main plus 45, okay? Go there. That is, yeah, that's where we want to go if the strings were not equal. And is it giving me that address? No, it's just saying main plus 0x45, which is, can we calculate that somehow? That's not very useful right now to me. Yeah, does it say that anywhere? Because I'd like to show you where that is. I guess we're gonna have to do it ourselves. Oh, here it is. It's 11AE. Excuse me. So yeah, it's a little bit, it's offset in domain, go to this address, because code is at addresses. So 11AE, we know that this is the start of the else case. Does that make sense? That's what's happening. So, yeah, let's save that. So this is the else case. So we'll get back to that. And then otherwise, if it didn't like take the jump, it stayed here. So this is the start of the if, right? Start of if. I hope that makes sense. So that's what's going on. Well, let's just keep on decompiling it to see what's happening, or reverse engineering. That's the start of the if. What is it doing? It is now loading the address into RAX of something. It's going to 2010. It's calculating the address 2010, and that's going to be another string. If you go there, it's going to be, that's our access granted string. See that? So it's loading the access granted string. So it's load string 2010, which is access granted. And then it's about to call puts on it to print it out, so it makes it the first argument. RDI is where it needs to eventually end up. Why they didn't just do RDI? Who knows? The compiler is a little silly sometimes. You can enable optimizations to make it faster and better, but like it's just being naive right now. So make that string the first argument. That's what it's going to do. And then this calls the printing function. To print out access granted, if you got it. And then you don't want to also fall through and print access denied, because that's what this code is about to do, right? Here it is doing other stuff. So it's just going to like always jump down to here, which is 11BD. That is like the end of the if else. Just going straight to there to start returning and returning 0. Does that make sense? That's what's happening. So this is just doing like saying don't fall through. Don't fall through and also do the else case. So yeah, we just figured out that the true branch is access granted, and we figured out which string we were comparing against. So like we essentially hacked it perfectly now. We understand. But let's just let's finish it off for fun. So what this one's gonna do, it's gonna load an address. This guy, which is 201F apparently, into RAX. That's the address 201F. It's the string that starts here, that A. It's the access denied string. Alright. That's loading string 2010. That's access denied. And let's see. And then it's putting it in the first argument, RDI. Make it the first argument. And then it's calling the printing function again. That's puts on that. And then it's ready to like return 0. It's happy and it's done. Like it moves 0 into EAX and then it returns after cleaning up the stack. That's what this instruction does. But that's how you reverse engineer programs and understand like what the password was. You can either like you can disassemble it, you could do a hex dump, maybe you need both, and now suddenly we figured out that, oh yeah, the password was, for our binary, it was password 123. Cool. And we get our access granted. Isn't that fun? So I think that's very interesting to me. There's another way to do this. And I want to show you that way too. So let's make another password hacking program. I'll call it password 2. And I'll steal a lot of the first one. Do a password 2, take that. And let's say that the password is correct if, we'll do something weird. The password is correct if argv of 1, that's their string. If the fourth character, address offset 3, right, 0, 1, 2, 3, the fourth character is equal to a C, then it's access granted. All right, there's my silly program. So that's called password 2. And again, we assume we just had the binary. We're not sure what the password really is. Like you give it something, it's like access denied. Access denied. But apparently the password is like whatever. You can put whatever you want as long as the fourth character is a C. And you can kind of figure that out. All right, you can kind of figure that out one way or another. And so I'll show you how to like figure that out. How to let's see. How do I want to do this? I'll show you how to like hack this one as well and like understand it. So let's see, what do I want to do here? Yeah, let's pick it apart and we will talk about it. And then we'll, I don't know, we can change them both as well. So let's see here. Well, let me just check my notes for exactly what I want to do here. I think that's fine for this one. Gosh. Yeah, I think I understand what needs to happen here. So yeah, let's just see what happens when we object dump this one. So I've got password 2. Let's pick it apart and like understand the code. Let's just do the normal reverse engineering way. And then I'll show you a way to do like to patch the binary itself and like change the code inside. All right. So that'll be fun. So here let's hack the password of this program too, just to have some practice. We'll say obj dump on its password 2 the binary, and I'll call it password2.s. So we'll take that and let's take a look at that now. So all right, password2.s. Let's open up the old, like the CPP program, even though we're assuming we don't have it down there. And then we'll do password2.s, the extracted decompiled assembly. And so here's the main function. Again, it's like setting up the stack as you know and love it now. And then here is, again, this is argc, this is argv, storing it into the stack. And then this is offsetting, right? This is rex equals argv. This is going offsetting and make it set to argv of 1. Rex saying rex plus equals 8 essentially. And so now it holds the address of argv of 1 because we're about to do not stir compare. Sorry, that's the wrong program. We're about to just like check for equality on characters. All right. So here it goes. It's going to take. It's trying to get the actual string out, so it's going to dereference rex to go and like give me the actual address of the starting string character. This is the address of like where the string starts. No, sorry, this is the address of where the string starts. We want to dereference once to get to argv of 1. So that this line does rex equals star rex. So now it holds the actual string argv of 1. So that's the pointer to where it begins. And then it's offsetting, going to offset 3. Do you see it doing that? There's the 3. So there's offset 3. 3 bytes later, the fourth character, right? This is rex plus equals, hopefully you're kind of understanding it, plus equals 3. So it's the address of the fourth character in the string in argv of 1. That's us, like leaving notes for ourselves. We're reverse engineering it. And then here it is, dereferencing that character and storing it into a smaller register called EAX. So it's going there, going to that byte value and like putting that character in a register. So like this puts the character, it says EAX equals star RX. That's what it's doing. And so EAX equals the fourth character in argv of 1. There it goes. And now it's comparing that thing, it's comparing that byte in the lower half of EAX called AL, compare it to 43, which is the hex code for C. Okay? So compare the character to 43 in hex, which is the C character. You can go look that up in the ASCII table. And it's like, all right, if it was not equal, go to the else case. Go to the else case, that's 1183. That is here. This is the else. Oops. Going here, that's the else case. So else. So this is, yeah, beginning of else. And then I think you can imagine what it's going to do here. It's going to take all this stuff. It's going to print access granted. Otherwise, if it fell through, if it was actually equal, it will stay going down here. That'll be the true branch. All right. So jump if not equal is like if not equal, print access denied. And hopefully you can kind of see what's happening. Like here's the beginning of the string. It's going to load the address 2013, that string, into REX and then print it out. So like this call here, this branch, is going to print string 2013, and we can figure out what that was. We can do xxd to hex dump the program, password2 to password2.hex dump, and we can go find what that string really was and make sure that it was access granted, confirm that. So there's 2 1000 colon, there it is. And so there 2013 is the string starting here, and there that is access denied. All right, so that's how I knew that. And then the rest for the true branch is same idea. Like if it was equal, we're still here. All right, and what this will do is it's going to load the string at address 2004 and say access granted. So this prints string 2004. That's my access granted. I hope this is making at least a little bit of sense. This is so fun though, right? There's where it begins, and like here's the C string, access granted, null terminated right there. All right, and that's just packing them close together to the other one. So yeah, we want to make sure that we get here, right? We want to make sure that we get there. So yeah, so we kind of figured out due to all this, like, all right, the fourth character better be a C, and that's how we hack the password. Like, all right, it needs to be hello doesn't work, but this would work. Helco with a capital C. All right, so that's granted if you put something there. So like that's one way to do it. That's how to reverse engineer. You can extract the assembly, you can understand the assembly. You can also combine that with patching over the program with XXD. So you can change more than just strings, you can change the actual code. Because like all these things, right? All these instructions, this is assembly code, they correspond to like at this offset in the file, it's these bytes mean do this. Does that make sense? It's like move RBP, RSP, that is 4889E5 in hexadecimal. That is what that code is in machine code. That's what the processor understands. It understands this encoding. And so like we can go look there. We can go find this instruction in the hex dump. Do I already have that? Let's go password2.hexdump. Let's go to address 114E. So like that's going to start at 1140. And go to 114E, that's right before the end. So EF right there. Oops. So it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. So there's the E part. So it's 4, 8. There it is. 4, 8, 8, 9. And then over here is E5. Do you see it? That is this instruction, and we can change that. Do you see the power that you could have there? So we can change that. Because kind of what we want, let's go back to the original password file. Let's go back to here. So like password1.cpp, like this one that was doing the string compare. All we want, like one way to break the program and like make it so that it's always access granted is just like to disable the check. Like the first way is to reverse engineer, figure out the actual password. Well, we could also just disable the check altogether. That would just like solve the problem as well, won't it? So password1.s. Do you see how the check happens for password 1 right here? Is this test, right? Is this test? It's like, all right, jump if not equal to the else branch. It's just like if it was not correct, it jumps all the way down to the else. It jumps to right here. And like the good stuff is right here. We want to get to here. So what we can do is just kind of like, we can delete this line. We can have it do nothing. Does that make sense? That's another way to fix this problem, to like hack the program. We could just say, all right, I just don't want to ever jump if not equal. I just want to make sure like this line does nothing, so that it just falls through to the true branch and always prints access granted. So if I could just change this to something else, then that will fix it. Does that make sense? That's the secret. And a good candidate for changing stuff is called a no-op. It's a no-op instruction in assembly. It's short for no operation. It's an instruction that does nothing at all. It just pads the assembly file with garbage, essentially. So it does nothing. It's called no-op. And let's see if that's somewhere in this file already. So here, no-op. There's a couple different kinds of no-ops. There's longer ones and shorter ones, and these are just really long ones. But take my word for it, there's a type of no-op that's a single byte long, and like there's different kinds. But the assembly for it is 90 in hex. So if I just replace my bytes with 90, they turn into no operation instructions that do nothing at all. All right, that's what I want. So what I want to do then is change this, where is it? This JNE, these two lines, this 75 and 11, change them to a couple 90s, 9090. Does that make sense? Because then it will not be a JNE anymore. It will be just like two no operations, do nothing, fall through to the true branch. Does that make sense? That's what I want, okay? That's what I'd like to do. And so we can do that in the hex dump. We can go and find this, this line, this 119B, it's 119, there it is, 119, and so it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B. All right, so it's going to be 75, 11, where is that? I don't quite see it. I think it's a bit offset, actually, isn't it? And oh, sorry, I'm in the wrong file anyway. This is password 2's hex dump. I want to go to password.hexdump, the original one. And so if I go to 119, so this one, do you see it? There it is, 7511, 7511. If I change those to 90s, that's what I want. All right, if I just fix that, then it will be happy. Let's see. Let me check my notes, make sure I'm doing the right thing. So yeah, instead of 7511 here, I'll change it to 9090. Does that make sense? That will work. That will change these into no operations that do nothing at all, and I can prove that to you. So let's take this file and call it, well, xxd in reverse, password to, oops, the password to hex dump file into password to, like, hacked. I'll call it password to hacked. All right. And so again, what we did is, oops, we changed this to 9090. If I split screen, I show that to you. Oh, I'm so sorry. I did it with password 2 again. It was this one. It was password.hexdump. I changed it to 9090 right there. So that's my bad. It was really supposed to be just password.hexdump. Sorry. Password hacked. There we go. And so that made a new program with that change. With that change right there. And here, let me show that to you. If I do objdump -d -m intel password hacked and look at it with you for the main function, I promise that there will be no longer that instruction at 119 whatever. It turned into no ops, you see? And so that's what it's going to interpret it as if I say password hacked. And I give anything at all. The original password was like password 123, right? That still works, but now anything else works. Isn't that cool? So I've hacked away the password check. I got rid of this test. Isn't that fun? I think that's fun. So there's that one. We can hack the other one too. We can be like, all right, same game. Play the same exact game on password 2.s. Where was the thing that was taking us to the else case or not? It was this one, right? This JNE again. Like, all right, if this was not comparing to a C, then access denied. But all right, if I just change these to 9090, it will skip this test and always hit the true branch. Does that make sense? So finally, we can do password 2 hex dump. So I kept accidentally doing that. And that's apparently living at 1170. So where's 1170? There it is, the 7511 right there. Change that to 9090. Get rid of the JNE, have it just fall through, do nothing. Does that make sense? That'll do it. So I changed that, and I can xxd in reverse now. I guess I already did it. I got it already in there. Password 2's hex dump into password 2 hacked. And now if I say password 2 hacked, like we figured out the right password. It's anything with a C right there. But now we're going to say password is CSCI, or we can say anything. It's access granted always because we skipped the check. All right, again, we can say objdump-d password 2 hacked and take a look at that. Where was the check? It was right here after the comparison, and now they got turned into no ops, so we're just following through, always only running the if case, the true branch. Isn't that lovely? So yeah, that's the other way to do it. You can patch the program itself, just disable the password check entirely instead of having to reverse engineer it and figure out what the password was. Just like find where the check was. Sometimes that's easier. All right. So yeah, that's hacking in a nutshell. I hope you understood at least a little bit of that. I'd be happy to help you learn more if you're interested in this stuff. Yeah, this is like the backbone of reverse engineering and cybersecurity. So I hope that you enjoyed this. I promise to not test you on it, But I think that is officially all that I have for this lecture. So yeah, I will see you in the next one.